Hello, welcome to another module in this massive open online course. So, in this module let us start looking at another digital modulation scheme, that is amplitude shift key. Okay. So, previously we have seen phase shift binary phase shift key. We will look at a different modulation scheme which is amplitude shift key. Okay. So, we want to start looking at a different modulation scheme, that is amplitude shift key or ASK. Okay, this is a different digital modulation scheme. Okay. And in amplitude shift key, so this is another, as we have already said, this is yet another digital modulation scheme. This is yet another digital modulation scheme in which we employ the pulse shape Pt equals square root, again a similar pulse shape, square root 2 pi fc cosine t for 0 less than equal to t less than equal to capital T, where capital T is the symbol duration and t equals k over fc. So, we have capital T equals the capital T equals the symbol duration, and it is also k over fc, which means basically it is an integer multiple, similar to what we have seen for binary phase shift keying. This is an integer multiple of the integer number of cycles. So, there are integer number of cycles of cosine 2 pi fct in the symbol duration. There are an integer number of cycles in the symbol duration, and we have already seen that energy of the pulse, if we look at integral 0 to t p square t, that is energy of the pulse. Previously in binary phase shift keying we have used a similar pulse. We have seen that energy of the pulse is unity. Okay. We have already seen this. Now, in binary phase shift keying, remember the symbol A naught can belong to one of two amplitude levels, minus A or plus A, and we said that both of them differ in the both of the waveforms, therefore differ in the phase. One of the waveforms, each of the waveforms is phase shifted by pi in comparison to or with respect to the other. In amplitude shift keying, both the waveforms differ in amplitude. Alright. So, while one waveform has an amplitude A, the other waveform has an amplitude 0. That is the whole point. So, the symbol A naught belongs to the set 0 comma A. So, A naught equals either A or 0. So, there is difference, waveforms differ in the amplitude. So, A naught can be either A or 0. Therefore, for instance, let us take a look at this. Therefore, the information bit 0, remember we have the information bit. Okay, so this is an information bit. The information bit 0 is coded as square root or a times square root 2 by t cosine 2 pi f c t, 0 less than equal to t less than equal to t, and information bit 1, this is also information bit, that is 0 times p t, which is simply equal to 0. For, of course, again goes without saying, 0 less than equal to t less than or equal to capital T. Okay. So, corresponding to the information bit 0, we are actually transmitting the waveform with amplitude A. Corresponding to the information bit 1, we are simply transmitting a 0 amplitude. Amplitude 0 means basically there is no signal. Okay. So, the transmission looks like, for instance, assuming k equal to 2 implies t equals 2 over f c. So, we have 2 cycles. So, basically this is, let us say, corresponding to the transmission of information bit 0, then corresponding to the transmission of information bit 1, we will have the transmission of 0, and again corresponding to the transmission of information bit 0. So, here the signal is basically, here the signal is basically 0, corresponding to amplitude, corresponds to amplitude or A naught equal to 0. Corresponds to amplitude A naught equal to 0. Therefore, if you can look at this, this is on, the signal is on in this region, or the transmission is on, transmission is off because amplitude is 0, transmission is again on. Therefore, this is also known as, that is ASK is also termed as on off key. This is also termed as on off keying. It is as if you are switching on the signal, and wherever corresponding to the information bit 1, the amplitude level is 0, that signal is 0. So, you are switching off the signal, again when the bit is 0, you are switching on, it is as if you are turning on the signal. So, this is also known as on off keying. Okay. Amplitude shift keying, where you are shifting the amplitude between two levels 0 and capital A, can also be, it is also termed as on off keying. Okay. Now, how to choose the energy A? We again come to the question, remember, how to choose the energy, how to choose A, which is the amplitude level. Now, remember, to choose A, assume we have to keep the bit energy. Bit energy is constant, we are keeping the bit energy equal to EB. Now, in terms of, for 0 xt, remember, for xt for 0 we are transmitting A times Pt, corresponding to information symbol or bit 1, we are transmitting 0. So, let us say this is if A naught equals 0, if A naught equals 1. Now, let us say again, let us assume a simple scenario, let probability of 0 equals probability of 1 equals half. Now, average energy per bit is equal to half, corresponding to 0, half a square energy in the pulse, plus corresponding to bit 1 you are simply transmitting 0. So, the energy of that will be 0. So, this is simply half a square E p. Now, given the average bit energy is E b, we need to have half a square E p is equal to E b or is equal to E b. Further, we have E p equals 1 because the pulse is normalized to unit power, which implies half a square is equal to E b, which implies, or which rather implies, a is equal to square root of 2 E b. And remember, this is important, we are doing this again to maintain a constant energy E b per bit across schemes. For instance, we had an energy per bit of E b in binary phase shift keying. We want to retain the same energy per bit E b for amplitude shift keying also. So, that will enable a fair comparison, enable us to make a fair comparison between amplitude shift keying and binary phase shift keying. Okay. So, that is the reason we are keeping the energy per bit as constant across the different modulation schemes. So this ensures the energy per bit is constant across the schemes. Now, as I have already told you, here we have 0 being mapped to A times Pt. I am formally stating this once again. 1 is mapped to 0 times Pt equals 0. Both the schemes differ in amplitude, that is, if you look at both the schemes, both the waveforms differ in amplitude. Therefore, this digital modulation scheme is termed therefore, this digital modulation scheme is termed as amplitude shift keying. Okay. So, that is basically amplitude shift keying or ASK, amplitude shift keying or ASK. Now, we want to calculate what is the probability of the resulting probability of error for this scheme or the probability of bit error. Okay. So, remember, we are transmitting xt is either A times Pt corresponding to information bit 0 or it is equal to 0 corresponding to information bit 1. At the receiver, we have yt equals xt plus nt, where what is nt? We have already seen what is nt. nt is basically, well, nt is additive white Gaussian noise. This is AWGN or This is the additive white Gaussian noise. Now, what is optimal processing at the receiver? Optimal processing at the receiver is we have to matched filter, we matched filter HT match filter with HT equals P T minus T, that is match filter, followed by sampling at T equal to T, followed by sampling at T equal to T. Now, consider y equal to, now consider the transmission of 0. Which means x t equals a times p t plus n t. Now, when you matched filter this is similar to again the transmission of bit 0 in binary shift keying. When you are transmitting a times p t, it is the same thing as binary shift keying where you are transmitting a times p t corresponding to the bit 0. Therefore, when you match filter this with h t equals p of h t equals p capital T minus t, followed by sampling at t equal to capital T where t is the symbol duration, what we get is, well, we get after matched filtering, or this is not x t, rather this is y t, so after matched filtering followed by sampling at t equal to t, or after match filtering what we get is we get R t equals a times E p plus n tilde, where n tilde is basically we have derived these before. I am using a lot of results from what you have derived before for the general optimal receive processing and binary phase shift keying scenario. So, n tilde is Gaussian with mean equal to 0, variance equals n naught by 2 times E p, but E p equals 1. So, you can also say this is equal to n naught by 2. Now, consider the information bit 0 or consider the information bit 1. Consider the information bit 1. When you consider the information bit 1, what you have is basically, well, x t equals 0 times p t, x t equals 0 times p t, that is basically equal to 0. So, you are not transmitting any signal, effectively not transmitting effectively not transmitting any signal. Okay. Now, therefore, what is R t? Therefore, y t is simply 0 plus n t equals n t. After match filtering and sample with sampling at equal to t, after MF and sampling at t equal to capital T, what we get is R t is simply, because there is no signal component, there is only going to be the noise, which is n tilde. Once again, n tilde nothing changes, n tilde is Gaussian with mean equal to 0. The variance equals n naught by 2 times E p. So, if you look at RT, and this is important, if you look at RT, you will realize that RT equals, well, A times EP plus N tilde if A not equal to A. This is simply 0 plus N tilde, or rather simply just say N tilde if A naught is equal to 0. Okay. Now, one can ask in this scenario, what is the optimal decision rule? One can ask, what is the optimal decision rule? Now, previously the optimal decision rule we said by symmetry, because we had mean shifted to minus A and mean shifted to plus, or mean shifted to rather minus A tilde and mean shifted to plus A tilde. So, by symmetry the midpoint is the detection threshold, but here this is not symmetric. If you can see, we have in this, in the first scenario, if you look at this, in this scenario corresponding to this, RT is basically Gaussian with mean AP. However, in this RT is simply N tilde, which means it is a Gaussian with mean equal to 0. The variance is the same in both cases. So, if you look at this, this is not shifted to minus A and plus A, but it is something very different. If you look at this, this is still two Gaussians. In first case the mean is 0, that is, or in one case, the first case rather, the mean is A times EP. This corresponds to bit the bit 0, and this corresponds to the bit equals 1. And now you can see the midpoint is not 0, but by symmetry again midpoint is AEP divided by 2. So, this is the Gaussian corresponding to bit 1, this is the Gaussian for bit equal to 0. By symmetry the midpoint is AEP divided by 2, which is the detection threshold, which is also the detection your detection threshold. So, by symmetry the midpoint is AEP divided by 2, which is also the detection threshold. Therefore, the optimal decision rule is not to compare RT with 0. So, the optimal decision rule is not to compare RT with 0, but to compare RT with this threshold A EP divided by 2, which EP is 1. So, this is A by 2. If RT is greater than or equal to AEP divided by 2, implies the decision is A naught equal to A. On the other hand, if RT is less than AEP divided by 2, decision is A naught equals 0. So, this is basically our, by symmetry, this is our optimal decision rule. Where we exploited the symmetry in the system. All right. So, basically what we have seen so far is we have started looking at different digital modulation scheme, that is amplitude shift keying, in which the different waveforms are shifted in terms of amplitude. One of them has an amplitude A, other has an amplitude 0. We have seen what is the amplitude level to keep the energy constant at EB, or the energy per bit constant at EB. Again we have seen what are the different received, what is the received symbol, what is the probability density function, or what are the probability density functions of the sample RT corresponding to the transmission of the waveform for bit 0 and the waveform corresponding to bit 1. We have seen that one is a Gaussian with mean AEP, where A is the amplitude level, EP is the pulse energy, other is a Gaussian with mean at 0. Therefore, by symmetry the midpoint is at AEP divided by 2, which is the detection threshold. If RT is greater than or equal to AEP divided by 2, then the decision is A naught equal to A. If on the other hand RT is less than AEP divided by 2, the decision is A naught is equal to 0. Okay, so that is the detection scheme. We will complete this in the next lecture and look at what is the resulting probability of bit error, and also how it compares with the binary phase shift keying scheme that we have described earlier. Okay, thank you very much.